We're now going to take a look at a thing called the boiling curve, and this was based on an experiment that was done by a fellow named Nukiyama back in 1934. And what this experiment enabled Nukiyama to do was to identify the different regimes in saturated pool boiling. So if you recall, that is pool boiling where there is no forced convection, it's just natural convection, similar to the stovetop experiment that we looked at in the first segment. However, the temperature of the liquid is at the saturation point or saturation temperature of the fluid at whatever particular pressure. Now, what Nukiyama did is he took a container, and he filled it with water, and he took the container or the water up to the saturation temperature, but there was a wire going across this container, and through that wire he sent a current, and by measuring the voltage drop and knowing the current, he was able to get information in terms of the heat transfer with that particular wire. And if we recall, power is equal to, that is going to equal the heat transfer from the wire is equal to IV, so the current times the voltage, P equals IV, power, Q is equal to IV, and also through Ohm's law, we know V equals IR, and from there we can obtain an expression for the resistance. That is going to be the voltage divided by the current. And so for his experiment, he was able to measure the voltage, he was able to measure the current, and from those two, he was able to compute the resistance. But with wires, the resistance, it's fairly easy to figure out what the temperature of the wire would be once you know the resistance. And so he used one of those relationships, and that enabled him to get the wall temperature, because the temperature of the resistor, or of the wire I should say, is going to be a function of the resistance. And so he used one of those relationships, and that enabled him to get the wall temperature. And he also knew the power going in, Q, and he knew the dimensions of the wire, and so he was able to get heat flux that way. So he was able to get Q over A as well. And this experiment is what we would refer to as being a power-controlled experiment. And what that means is he was able to vary the current going through the system, but he was not able to vary the temperature. The temperature just occurred based on the voltage and the current flowing through the wire. And so he was able to control the power going in, but he was not able to control the temperature of the wire. So what we're going to do, we're going to take a look at the boiling curve that Nukiyama was able to get by conducting this experiment. And it will give us a lot of information about saturated pool boiling. Okay, so this is a curve, the boiling curve. Now, Nukiyama was not able to get this entire curve. He was actually unable to get this section here, and that would only be, you'd only be able to get that if you were to do a temperature-controlled experiment instead of a power-controlled experiment. But a few areas or points that I want to point out, and then we'll describe other ones throughout the rest of this segment. But first of all, this point up here at point C, this is the critical heat flux. And that had a value of Q max double prime. Another one is down here at point D. This is where we have the minimum Q, and this is called the Leidenfrost point. And the Leidenfrost condition, if you've ever taken a droplet of water and put it on a really hot stove, you see that it kind of bounces around and skips around. And it's because a vapor develops underneath the droplet, and consequently it is free to move around. And that is the Leidenfrost point there, where you have a vapor between the solid and the liquid. And other things that I want to point out, from a delta TE, remember that's the excess temperature. If we look from 1 to 5, so in this range right here, this is referred to as being free convection heat transfer. And what is happening there, just like the video we watched when we saw the natural convection taking place in the pot before the bubbles started to form, that's what is happening between 1 to 5 with the excess temperature. And then we go into a region that goes from an excess temperature of 5 up to 30. We get a new regime forming in there. And so this would be where we have nucleate boiling. And so what is happening there is bubbles are starting to form at nucleation sites. And from 5 to 10, those are isolated bubbles. Let me do that with a different color. So from 5 to 10, in this range here, those are isolated bubbles. And then from 10 up to 30, that is where we get another process taking place. And that's where the bubbles start to coalesce with one another. And what we then get are jets and columns. And so you could see that in the video as well. The bubbles would start to communicate with one another and connect, and they move up into pillar-like structures. Now, when you're watching in the high speed, it didn't look that way. And that's because you do have isolated bubbles going up, but they do connect into one another with the wakes that they have behind each of the bubbles. So this is a region where we have jets and columns. And then we get up to the critical heat flux point. We then move into a regime that Nukiyama was not able to investigate, and that is going up to the Leidenfrost point. And I said that he wasn't able to do it because he did a power-controlled experiment. He would have had to have done a temperature-controlled experiment in order to investigate that. And this region is referred to as being transition. And what's happening here is we're starting to get a film forming around our surface. And so we get bubbles moving into a film. And then finally, when we go above the Leidenfrost point, that's when we have film boiling. And then radiation becomes very important, but we'll be looking at that and describing it as we go on through this segment. So what I want to do, I'll refer back to this plot, but this is the boiling curve, and we're going to look at each of these different areas, and I'll provide a description for each of the different temperature differentials. So to begin with, we had free convection. And that's for excess temperature less than 5. And here we saw that this is just natural convection taking place within our pool. And then, let's see, did I put this on the curve? ONB, I did, good. Okay, this is the onset of nucleate boiling. That's what ONB stands for. And essentially what that means, bubbles. Bubbles start to form. And sometimes they make it to the top, sometimes they don't, but they start to enhance the amount of convective heat transfer on the surface, because remember I said bubbles, as they move up, they entrain liquid from around them. And so we can move through isolated bubbles. That's where we will start. And we saw this in the video. We had isolated bubbles forming. And this is when we our pot started to make noise, and so you could hear it with the sound. And what was happening is bubbles would form, and sometimes they would then collapse if they didn't have enough of a temperature. But the range here, anywhere from excess temperature of 5 up to 10. Those are isolated bubbles. And then we moved into jets and columns. They appear to be jets and columns, although they could be discrete bubbles, like I said before. You can see that with a high-speed video, which Nukiyama obviously didn't have when he did this experiment back in 1934. Got to give these guys credit for the amount of information they were able to extract with such rudimentary equipment. They didn't have cell phones to distract them all the time, so they were able to focus. Okay, so those are jets and columns. And then we get to point C. Point C was the critical heat flux point. And in the next segment, it will become a little more evident why we call this critical. And this is for delta TE approximately 30. And when Nukiyama was doing his experiment, this is where his experiment went a little sideways and things didn't go very well for him. And I'll talk about that in the next segment. And then we move into transition boiling. So we would only be able to get here if we were doing a temperature-controlled experiment, not a power-controlled experiment like Nukiyama. And this is delta XS, delta TE, from 30 to about 120. Hopefully that's what I had on the plot. Let's see, 30, yeah, that's not too bad. Transition, that looks like about 120 right there. Okay, I was estimating a log scale, which is hard to do. And what is going on here is we're starting to get an insulating layer of vapor forming around our solid. And what is happening is the bubbles are forming, the vapor is forming, and they are coalescing and starting to form this insulating film of vapor. Obviously, I was not able to get that on the stovetop because we remained in jets and columns and individual bubbles going up. And this is where on our boiling curve, Q double prime, or the heat transfer, is actually reducing. And this takes us to the Leidenfrost point. But if you were to look at your wire, what would happen is you start to get bubbles that are connecting with one another. And so around this is for Nukiyama's experiment, we get this film. And so connected here might be the bubbles coming out, but they're all starting to merge with one another. And when they do that, you get this insulating film. And this insulating film is the vapor itself. And with that, you're not being able to bring in liquid in order to bring the surface back through the convective processes that we were looking at before. And so convection becomes less and less being the main form of heat transfer. We start moving into radiative heat transfer. And then eventually we go through transition boiling, and as you increase the temperature, the excess temperature, we get film boiling. And that would be for excess temperatures 120 degrees or more. And so when we get up into this range, what happens is any kind of increase in heat transfer, looking at our boiling curve, remember we came up, we did this sort of a thing, we come down and then we do that, where we're talking about this region in here going up. And so what's happening, this is our critical heat flux. This is where we were in transition. And then here we have film. And so what's happening in this film region is the increase in heat transfer is due to radiation. Because if we look at our wire would be completely blanketed with this vapor film. And consequently, the convective heat transfer has been minimized, and the temperature of the wire is going up. and then it becomes radiation, radiative heat transfer. And so our temperature, if you recall, this is delta TE here, can start to go up relatively quickly as we increase the heat transfer watts per square meter. So that is the boiling curve, and what we're going to do in the next segment, which will be the last one for this lecture, we're going to take a look at what happens when you operate in this zone and the troubles that it caused for Nukiyama when he was doing his power-controlled experiment.